start recording this one for the others. Right. Last week, remember, we were talking about coordinate systems, and we basically talked basically about two types of coordinate system. One is called the equatorial coordinate system, and the other one is called altitude azimuth coordinate system. And if I summarize that, I told you that altitude azimuth coordinate system is somewhat more suitable for local observing viewing, which means that if you need to locate an object with respect to you in your location, it will be easy. But at the same time, this celestial coordinate system, equatorial coordinate system is the coordinate system that we use globally. So which means that coordinate will not change depending on the location of the observer, right? This is why the equatorial coordinate system is more important, and the measurements are taken in terms of right accession and the declination. And also we talked about something called ecliptic, which is the path of the sun on the sky. And that particular, the relevant plane is called the ecliptic plane. Right, so let me start today's lecture first. And the screen actually that you show just at the starting point of your lecture is the software that I frequently use, which is called as the Stellarium. And this is a completely free software. You can also use the same if you like. Just go to the, I think I gave the link last time for you. Just go to that site and you can download it. From time to time, I will use this software to explain some of the things, right? Let me stop sharing this and go back to my presentation. So I'll be sharing my presentation right now. So I would assume that all of you can see my presentation right now. And so this is a continuation of the last chapter, by the way, right? So this includes in the same chapter. So today I will be basically discussing about the seasons we have, how seasons occur, and how you can explain it with the knowledge that you have in astronomy. And at the same time, I will be trying to explain you some of the terms and how astronomers keep track on time. So there is something called sidereal time or sidereal time. Some people call that sidereal time, and the solar time. So there is a slight difference between those timekeeping methods, and I will tell you why, and then you will also understand why that you should know that is important. The outcome is that once you have a good idea about these two timekeeping methods, you can actually predict when is a particular constellation up in the sky will rise or set, right? So that is the advantage, and also for other objects as well. And next I will start, if time permits, I will go through a little bit about the different phases of the moon. And also at the end, there are two other sections I want to talk, which is about basically about solar and lunar eclipses, if time permits. If not, we will talk about those in the next day, right? Right. Now the first thing is, so I'm starting with the seasons. Now this picture that you are seeing here is captured with the fisheye lens from the Atlantic Space Shuttle on December 9, 1993. Now, this is like Earth hangs above the Hubble telescope as it is repaired. Now, the continent that you are seeing on the Earth is actually the Australia, and because of the features of the lens, the size is bit distorted. So I just, you don't, this picture is actually not that much important for you. What I want to tell here is just to give you an introduction that because the Australia is in the southern hemisphere, so it's a country or a continent that is located in the southern hemisphere. Uh, it is summer in Australia in December, right? Now, if you are little familiar with seasons, you know that in December we normally have a bit colder weather, but we don't feel it that much. But if you go to the northern hemisphere countries like Europe or any other country like Canada, you will see, you will of course feel the winter, and you will see that in the news these days. You will see under weather, you will see a lot of winter storms as well, because now it is the winter time for these northern hemisphere countries, and at the same time it is summer for the countries like Australia, right? In December 9, you can see that from this picture, it is the summer time for Australia, which is a country that is in the southern hemisphere. Now, this difference, we don't feel this different that much, so our weather seems to be like pretty much similar throughout the year. Actually, the reason is that we are very close to the equator, so that we don't feel that different that much. But the other countries in the two ends of the hemisphere, the northern and southern hemisphere, will feel this, right? Now, let's look at how the seasons occur, because I want to explain this a little bit, because some of the students and even some of the public community also has a different idea about the reasons for season, right? Now, if you look at the Earth's orbit, it is, I mean, we used to tell that it's an ellipse, but its eccentricity is very small. So which makes that we can assume that it is nearly a perfect circle, right? And also in Earth, the question that we have to answer is why it is hotter in summer and colder in winter in many places. You can see that when we say winter, it means colder, and when we say summer, it is hotter. So there should be a reason for that, right? Now, most people believe that the seasons are a result of changing distance between Earth and the Sun. You know that when this Earth moves around the sun in this elliptical path, there are 2 points that Earth is very closer to sun, right? And the other two ends are far away from the sun. And because of that, some people used to believe that the seasons occur because of these changing distances between Earth and the sun. And believe me that even after I teaching this course, sometimes I used to give this basic question for students in exams, then they also believe the same even after learning astronomy. Maybe they were not in lectures, but this is not a good thing. So make sure that you get this scientific reason, right? Now, the problem is, if this is true that the seasons occur because of the changing distances between the Earth and Sun, then the next factor that I have mentioned here in my presentation, that is actually, let me show this to you. This factor right here, the Earth is actually closest to the Sun in January, right? When the northern hemisphere is in the middle of the winter, right? So which means that that fact is not valid, right? Because January is the time where you are hardly hit by the winter. Normally in all these northern hemisphere countries, which are far away from the equator. So at this time, Earth is very close to the sun, right? And you can see that due to this reason, we cannot accept this. Now, so I have highlighted right here the actual reason for having different seasons is the tilt of the Earth axis. So make sure that you get this point, right? The seasons are actually caused by the tilt of Earth axis. Remember the last week we talked about this. There is a tilt of Earth axis at 23.5-degree tilt, and that tilt make these changes of seasons. So that is the primary reason for having different seasons. Now, remember that we actually talked about this tilt is also this tilted angle is also make a precision, which is happens for every 26,000 years. But we don't want to talk that here because we are just looking at short period of time, how the seasons occur in each year, right? So this diagram nicely explains actually what happens, and you can see uh, in let's look at starting from March 21st, and you can see the sun is right at the center, and then you have Earth going around the sun or moving around, orbiting around the sun. And this when Earth is orbiting around the sun, you can see this tilted angle, right? And when Earth is right here, you get which is the date we called as March 21st, or the vernal equinox. And this point right here, this is September 21st. So these are the two positions where the sun crosses the Earth's equator, right? If you look at the motion of the sun with respect to Earth, at this point, what happens is the sun crosses the equator and moves into the southern hemisphere direction, which means towards, in this diagram, it should be in this direction right here. So you can clearly see that when it moves to this direction and is right here, all this part in the southern hemisphere, they get direct sunlight to this region. So they get direct sunlight for some time. So that's why they have summer close to June 21st, because June 21st is the date that where the sun is up in the most highest sun is so June 21st is actually the date where you have the sun goes very high close to the northern hemisphere, right? And around this time, for all these countries close to the northern hemisphere, I mean like this continent that you have uh, right here, and all these regions that are in high altitude, they have sometimes 24-hour sunlight. So the sun never set in those regions at this time, because the sun is up right here and you get sunlight, complete sunlight to this region for some time, right? And then the sun goes down in this path, and when it comes to here, again, this is the point you get the autumnal equinox, which means now the sun has gone down again, crossed the celestial equator at this point, and then it moves towards the uh, southern hemisphere direction. Now, when it moves to the southern hemisphere direction, then all these countries right here in the southern hemisphere, they get direct sunlight from the sun. So that's why they have summer in the months of December and January. And we call this as winter solstice, right? Now, this is what I have explained here. Under seasons, we see Earth at different seasons as it circles the sun. In June, the northern hemisphere leans into the sun, and those in the north experience the summer and have longer days. In December, during winter, in the northern hemisphere, the southern uh, hemisphere leans into the sun and is illuminated more directly. In spring and autumn, the two hemispheres receive more equal shares of sunlight. So it is these 2 points actually. So this one and this one right here is where you have the spring seasons. Sorry, not those 2 points. This one right here, March and then September. So those are kind of seasons that you get like equal amount of sunlight to both hemispheres, because the sun is just crossing the equator, right? Which means kind of equally, sunlight equally goes into two directions. And then this diagram right here shows now why uh, it gets hotter in summer and colder in winter. And in the first diagram right here, so that's how the sun appears, or sun appearing very high in the sky when it comes to the summer, and you get this direct sunlight, right? When you have the angle of sunlight is very small, which means in the angle is actually larger compared to the ground, which means you get more direct sunlight in the summer time, and sunlight doesn't spread out. So which means the surfaces get more hot at that time. And in winter, the sun is very low in the sky, because you can see that, for example, if you are in a country like Canada, in the month of December, the sun goes down to the southern hemisphere, right? So when the sun is in the southern hemisphere, you get some sunlight, but the angle that you get is very small, right? So the sun is very low, so the sun moves very low in the sky, so it doesn't come up high in the sky. So when this happens, the amount of sunlight that falls into the ground is the intensity is very small, right? Because of this angle is smaller, right? You know that even in basic optics, this is the case. If you get direct sunlight, direct light from somewhere, then you get more energy. If it is angled, you only get less energy, right? So there is this basic principle here, right? Now this diagram nicely shows you the length of the time that sun spend above the horizon. Now this is actually, we can't experience it that much in our country, but in these days you can see that when it comes to the December last week and for the January first week, the sun goes down a little bit earlier, right? I mean, if you are in, maybe if you are in Jaffna, you may feel it a bit better than us, because you are a little bit up in terms of the uh, location, right? Close to the, at least a bit closer to the northern hemisphere. So what you should experience is actually, in these days, the sun goes down earlier, right? So you will get only less amount of sunlight, because we are also in the southern hemisphere, northern hemisphere. But this effect is actually huge when we go into the northern countries. Now, for example, I have this personal experience that I have lived in a Canadian border, and we just don't get any kind of sunlight after 4:30. I mean, when it gets 4 o'clock, it's really dark. So it's really like you are living in night. So you get almost like how many hours? It's like you get 13 or 14, maybe 15 hours of night time in December and January months, right? And you really feel it, and you can see that the sun just goes very low uh, on the sky, so the sun doesn't come up high in the sky at that time. Now, this diagram explains that when it comes to uh, June 21st, right here, the sun rises north of east and set north of west. So that means uh, this diagram right here, you can see that thing that you are sitting right here, and here is the sun from the yellow color, and sun rises from this side, and then so it should be north of east, and sun rises north of east and set north of west. So you can see that sun rises from here and then go into this path and set from here. You can see that with relative to you, when you are right here, the sun appears a large amount of quite a bit long. I mean, sun appears up in the sky for a long time. And when you go into this time of the year in the second diagram, on March 21st and September 21st, now what happens? The sun came down to the equator, right? When you go from equator in this path, you have equal day and night times, right? And in the opposite hand, when you are right here, you can clearly see that when you come to the December, when the sun is in southern hemisphere, you can just see that the sun goes up here and then comes down here very quick, right? So sun is like very low up in the sky relative to you, and the sunlight that you get is a very small amount, right? So these are, I mean, these three diagrams very nicely explain it. And if you, I will upload this presentation, so just check the diagrams and you can easily understand this. And the sun's path in the sky at different seasons that I have explained here. And for observers in the northern hemisphere of the Earth, sun spend about 15 hours. So that's what I told you above the horizon in the United States, meaning more hours of daylight. This is the first diagram. And on December 21st, the sun rises south of east and sets south of west. That means uh, south of east is right here, south of west is right here. So it just go very low in the sky for this winter time. I guess you can understand it even itself from this diagram, right? So that's about season. So I hope you understood the idea behind this, right? Now, actually, the take-home message here is this thing right here. So make sure that you know that the exact reason why you have seasons, right? As science students, this is very important. And also you should be able to explain how seasons occur for someone, right? Now, even for you, if you look throughout the year, you can see that the sun appears, sun rises, sun doesn't rise and set from the same place, right? So it is different. So it moves a certain amount and then goes, I mean, sun actually goes a path like this, right? So it goes into this way and then moves again up to here. So if you look uh, the eastern sky when the sun rises, this position changed over time. So if you can locate, let's say where it rises tomorrow, and then go and look at the same thing like after 3 months, you will see that it is not the same position, right? We used to tell that the sun rises from east and set from the west, but exactly it is not rising from east, right? So it changes a bit over the time. And that change is actually very larger for these northern and southern hemispherical countries. Right, so that's the section about the seasons. Now let me explain a very important concept about timekeeping in astronomy. Right, so this is one of the very important concepts that you should know. Uh, that is the idea about the solar day and the sidereal day or sidereal day. Right? Now this came from the fact that I will also work some examples with you for this one as well. Now, the most fundamental astronomical unit of time is the day. So the day is what we normally use to measure, right? So it is like a fundamental astronomical unit for timekeeping. Now, all of you, I guess, know that what it means to have a duration of 1 day, right? So this is based on the rotation of the Earth. I mean, roughly one rotation will be equal to 24 hours, and this is what we called as a day, right? So that is the normal definition. Now, if you look at the solar day, I mean, there is a slight difference between these two things, which we called as the solar day and the sidereal or sidereal day. The difference is that the solar day is slightly longer than the sidereal day, right? That is because Earth must rotate an additional amount equal to 1 over 365 of a full turn. The time required for this extra rotation is 1 over 365 of a day, that is about 4 minutes. So what this means is actually for solar day, you have 24 hours, but if you consider a sidereal day, you will have 23 hours and 56 minutes. So there is a 4 minutes difference, right? The solar day is about 4 minutes longer than a sidereal day. Now, the reason is that right here you can see in this diagram, which explains the difference between this sidereal day and a solar day. The sidereal day actually is, you can see that there is a white arrow that is pointing towards the left side from the earth, and earth rotates. But the thing is that while earth is rotating around its own axis, it also rotates around the sun, right? Which means after day one, let's say now it has to be pointed again towards the earth, right, to complete the day. So what happens is it rotates this amount, and while you see it is rotating and going to day two, it will be maybe right here. So it has moved a degree, close to a degree. So which means it has to rotate a little bit more to point towards again the sun, right? Now this is what caused that extra 4 minutes, right? Which we called as the solar day, right? So that's what I have mentioned here. Uh, because the earth moves around the sun after one complete rotation of earth relative to the stars, we do not see the sun in the same position because now we have moved little bit, right? So you have to angle the bit more to make that circle, right? So that's what means here, and this is called a solar day, which is what we have as 24 hours. But for the sidereal day is actually is measured with respect to background stars. If you consider a distance star, let's say like Aldebaran, I don't know whether you know about it. Aldebaran is one of these bright stars that you would see one of these constellations. As far as I remember, this should be in Canis Major constellation. So if you compare this rotation with respect to one of these stars, that will be actually 23 hours, 56 minutes only. So that it will be 4 minutes earlier. Now, if you go for like real time observing as an astronomer, astronomers prefer sidereal time for planning the observations because of in that system, a star rises at the same time every day. There are a lot of stars now. Now we are concerning only about the sun as regular people, right? So what is important for us is the rise of sun and set to keep our living. But for astronomers, it's not the case. We are looking at other stars. So star rises at the same time every day if we use this sidereal time. So keep an eye on that, that you should be able to convert uh, between these two times, right? Let me give you an example here. Now I will give you some time to think about this, and after that we will discuss. Assume that the bright star Sirius rises at 7 p.m. from a given location so that by midnight it is very high in the sky. And you can see the scenario here. The Sirius is one of these bright stars. It is going to rise at 7 p.m. from the horizon, and which means after 4 or 5 hours, when it close to the midnight, it will be right up, very close to above your head, on the very close to the zenith, right? The zenith we talked last time, right? Zenith is the point directly above your sky. And so what you need to figure out here is at what time will this particular star rise in 3 months, which means after 3 months, at what time this star will rise. Now this is where this sidereal time is important, right? The only thing that you have to think here is there is a 4 minutes different between these two times. Okay, so let me give you some time if you like to think about this, maybe a few minutes, and I will wait. And if anybody has an answer, you can post it in this chat window, right? It will be interesting to see whether you grab this concept. I mean, this is a very simple thing, but see, it is a nice thing to know that when you need to locate or decide about the objects without the help of others in the sky. Right, so I will be silent for a few minutes. So I will let you think about that and then post your answers in the chat window. Right, so let me just, right, so once again, the answer for this one is actually why for each day you get a 4 minutes different, which means 90 times 4 minutes, that will be 360 minutes, which is equal to 6 hours. That means this particular star will rise 6 hours earlier after 3 months, right? Right. So I got a message that my voice is not clear. Is it clear now? I guess it should be, right. And can someone confirm me that you can hear me clearly? It seems like there is an issue here. Just give me a minute.
Yeah, sir, we can, but the weather is not good, so might be network connection
Oh,
for.
okay. I understand. Yeah. So I will actually post the recorded one quickly. Since right. So I guess all of you put this particular example. So I expect that I expect that you should I mean from you that even in exams you should be able to solve these type of simple problems, right? This is like practical astronomy. I mean, if somebody asks you if you can see this particular constellation after 3 months, you should be able to answer by just considering about the sidereal time, right? Now, as an example, let me show you something from the software that I am using, Stellarium, which we can see this in real time. So let me stop sharing this for a moment and go for the Stellarium software. Right. So I would assume that you can see my software right here. So this is the Stellarium software. And you can see that in real time, this is right now how the sky looks like for me. And you can see that sun is just setting on this between west and southwest, right? Right away, you can see that we used to tell that sun used to set from the west, but it is not the exact position, right? Now this is little bit deviated now. That's because we are very close to the January. Now, if I uh, make this software forwarded for a different day, then actually that will be different. But my aim is now is to look at one of these. Okay, Sirius is right here. You can see this is the Sirius star. And let me, so once again, I am actually sharing my Stellarium software with you. If you can't see it like the last time, please let me know, right? So I hope you can see it. According to my screen, it seems to be it is properly shared now, right? So Sirius is right here. What I can do from this software is actually I can take the time back from here to look at. It's going too fast now. So I'm taking it backward. You can see that it's going backward right now. I'm going to stop it right at the point that it. So this is the point where it rises, right? Now the time is, if you look at the lower right hand corner, the rising time of this one is 5:48 right now. It's clear from the 24-hour clock, 17:48. Now let me advance this into 1 month, right? So that means it is January 10th right here. So if I can change this to, see if I can change the time. So I'm going to advance it to a, sorry, too much. So I'm going to advance it to like for, let's say 3 months. Today it's January. So I'm going to go it for a February, maybe March and April. Okay, so it's now May, which means 4 months after now. So let's see at what time this particular star is rising, right? Let's see whether I can find it. And see that the sun goes down, and I expect that the star will rise very late. Right? So it rises at 1, which means 1 or 12, which means let me see, yes, it should be daytime then. Right. So you can see the Sirius is right here in the month of May, right? Which means around 6:51, it is already close to setting from the west side, right? So that means this star should have risen above the horizon very early in the day, right? Around 11 or 12. So that's what we had from this calculation, right? So when that happens, the star actually rise at around like 11 or 12 in the daytime. So it will up in the sky on the daytime, which you can't see. When it comes to the night, it is already close to the horizon again on the west side, which is trying to go down from the western sky, right? So that's what has happened. And you can see that it's interesting to see that all these objects like the Betelgeuse, which is actually the it belongs to this Orion constellation. Right here, the Orion constellation right here, right? If you go today up in the sky, you can clearly see that around 7, 8 or 9 Orion constellations is right up on the sky. But what has happened is after 4 or 5 months, because of this difference between the solar and sidereal day, the Orion constellations has also risen at daytime. So it's setting very early, right? So this is how people used to one way of locating objects. Now, if you see the Orion constellation right now up in the sky, and if you plan to look at the same constellation, let's say on the month of April, you should actually see the western sky just before the sun rises because of this. You can do this calculation using the sidereal time, right? So this is what I want you to learn here. So if I, let's say, give you a problem in an exam asking that, okay, this constellation rises on the month of January at 5 p.m. in the evening, and I'm asking, okay, what time it will rise? Oh, I will ask whether can you see this constellation up in the sky after for 5 months? Then you should be able to do the calculation, this small calculation, and tell me that okay, you can't see this particular constellation because of this reason. The reason is that it rises very early in the daytime, and it will the star will also set uh, very early. I mean, when it gets dark, sky is already close to the western horizon, so that you can't see it, right? Now the same thing. This is what you may remember that the people used to talk about this great conjunction of Jupiter and Saturn, but they said that you have to look at the western sky, right? Because they are very close to set, because they have also already risen up in the daytime, so they are close to setting set uh, from the western sky when it comes when the dark time starts, right? So that's why most of the people could not spotted it. But if you look at from the naked eye, you can still see it because the Jupiter is very bright and also the Saturn together, right? Right. So that's what I want to explain using this particular software right now. Let me go back to the lecture again. So I am going to share my PowerPoint presentation again. Oh, I think I didn't see that. Is that my, yes, my, actually my location has set to 2026 for some reason. Uh, However, you will see the same thing even, I mean, this is because maybe I went too fast earlier. You can see that you can see the skies even after 5 years, 6 years, and you can go back up to hundreds of years from this one, right? So I was just thinking to finish this quicker, and then maybe I went a little bit faster. But for each year, it will be the same, by the way. So you will not see a difference. So let me see whether I can take it to the point where for the 2020 again. You see, I guess this takes time. So I guess you can do this yourself. This is not a big thing. And also, I guess this screen, we may have not seen that as well. All you need to do is just go back and manipulate through the software and change the year, but you will not see the difference, right? But each year you will see this pattern through the constellation, right? Because you make a one circle, no, the Earth will be in the same position after 365 days, right? So that's the idea. So it's just a month that is important, but just download the software and work yourself. So I'm uh, just not going to do it. It takes time, so I need to finish the presentation. Right. So I have a question right here that is very similar to the previous one. Just try it yourself. If a star rises at 8:30 p.m. tonight, approximately what time it will rise 2 months from now? So this is very similar to what we have discussed earlier, right? So just think about this time difference, 4 minutes for each day. So that's all you need to consider, right? So just try it yourself. This is just a sample problem that you could try, right? So now I want to talk a bit about the constellation. So that is about the seasons and the things that sidereal time and the solar time. Now I will be move on to talk a little bit about the night sky and the constellations. Now, on a very dark, clear night, it is possible to see several thousands of celestial objects in the sky with the naked eye. So, what this means is if you go outside, let's say today, I mean, you said that it's raining, so it may be not a good time. And if you go in a clear night outside, you will see very clear skies. If you are in a very dark place and if the sky is clear, then you will see thousands of uh, objects up in the sky. Now, almost all these objects that you are seeing up in the sky, probably except the moon, actually are stars, right? And there are one or two planets. For example, like you can see Mars these days. Other than that, almost all of these objects are stars. Now, if I ask you a question, are these stars are in our solar system or it's in a different outside our solar system? Do you know the answer for that? And maybe you have issues with the connection, so I will just continue with the lecture. The question answer is actually all these stars that actually you are seeing in this sky is actually not inside our solar system, right? So only star that we have is our own sun, and all the stars that you see in the sky are actually outside our solar system, not within our solar system. And most of almost all these stars are actually belongs to our galaxy, right? Most of them are, right? And there are many more stars even that are beyond the Milky Way, right? So that's what I have mentioned here. I mean, these are just the practical things that you probably should know. Very simple things, but still it's worth to know these things. The stars are similar to those stars that you see are actually similar to sun, uh, except the fact that they are actually much further away. Right? If you bring those stars very close to us, you will see that they are some of these stars are brighter and even more brighter than our own sun. Right? There are calculations that we can show those things. We will talk about those star magnitudes and brightnesses when we start talking about the stars. Right? This is just a chapter about the naked eye observing things that you can see up in the sky. And because these stars are actually further away from us, they look much fainter, right? You know that. And all of these stars that you are seeing actually part of our own galaxy, as I said, right? Which is the Milky Way. So the stars that you are seeing once again are in our Milky Way, right? That does not mean that there are no stars outside the Milky Way. Actually, most of the stars are outside the Milky Way, right? In other galaxies. And but the thing is, they are actually too faint to be seen with the naked eye. Right? You can't see it from here with the naked eye. The stars that belongs to uh, the other galaxies outside the Milky Way, right? So that's the thing. So many more stars that are beyond the Milky Way, and they are too faint to be seen with the naked eye. So that's something that you have to uh, keep in mind. Right. So this is just a picture of a sky. You don't have to see this. Just go outside in a clear night, and you will see a similar picture, right? And the thing that you need to know is, as astronomers, you should be able to see these, understand these constellations that up in the sky, right? The way to get an idea about the constellation is just go outside and look at the sky. There is no other way of learning this, right? Just looking at the lectures and the things in the notes will not uh, teach you the whole thing, right? You will get a lot of things, but this practical experience, you have to go outside. And I would recommend that, I mean, if it is safe, just go outside in a very clear day and look at the sky and to try to locate these one or two constellations, right? Which is like really interesting. And then you will get used to it, right? Now, these constellations, which is actually one of the popular astronomy from the ancient time, popular section of the astronomy in general, these stars actually in the constellations that you see, they seems to be very close to each other, right? And so the stars do not appear to move noticeably with respect to one another, and these stars also do not move with respect to each other. There are no noticeable movement, right? And because of that, these patterns are recognizable very easily, as you saw in the stellarium software. For example, this pattern of constellation Orion is very easily recognizable for everyone, right? And these patterns are what we actually called as constellation, right? Now, many ancient civilizations that we had in the past identified and named a wide variety of constellations like this. And right now, there are actually 88 official constellations that we have, both in the northern and southern hemisphere. And some of the constellations that are very in the southern hemisphere, we may not be able to see. And there are certain number of constellations actually we can see, right? Now, as you see in the stellarium software, if you go and look at it, there are very clearly some of the constellations that you can even see in today's sky. Not even today's, in this month and the next month you will see those. But they will gradually go down uh, and disappear from us due to the reason that we have discussed earlier, right? Now, uh, for example, if you go today's so let me change this time to right today's. Now this is the sky looks right now, how it looks like. Right. This is, I assume that you can see this right now. This is how the sky looks like right now up in the, if you go outside, if the sky is clear, if you are in a place that you don't have rain and skies are clear, this is it will be slightly different because the location difference, but it is pretty much very close to what you see here. And these all these lines are actually constellations, right? And here is a Gemini. It's one of the constellations that are very popular. And then Arsame, Mass is right here, by the way. It is not our talking point today. And Sirius is right here in this constellation. Right. So I guess this is Canopus. I can get the constellation names here. So Sirius is actually the constellation of Canis Major. And then what else? Gemini is here and the Orion constellation here. And all these constellations you can, if you go outside today, you can, it is easily visible. And Andromeda is right here. And if the sky is clear, the Orion is one of the constellations actually you should look because it's easy to visible, right? So all these are constellations that you can see up in the night. Let me just go back to my presentation. I mean, just use the software and you will understand this stuff. And there is one important point about constellations that I want to mention. I mean, it seems that these stars are very close to each other, right, in terms of this pattern. But the truth is actually the stars in these given constellations are usually not physically close to each other in space, right? They are just a chance of alignments of stars that lie at different distances, right? Because we just, it seems like when something is very far away, you can't identify the difference between the distances, right? It seems like they are in the same plane. But the truth is they are not actually, they are far away from each other. Because of these huge distances, it seems like they are in the same plane and very close to each other, right? Now, this is something that you should note, right? The stars, they are just a chance of alignments with different distances, right? So this is normally this is the Orion constellation, by the way, which I have discussed. And uh, there is something called constellation boundaries that you can put again in the software and identify the constellations. And this is just an example of a constellation. And I expect that when you see this picture after your astronomy course, you should identify, okay, this is the Orion constellation, right? You should have that knowledge. And this is something actually I cannot uh, like force you to do. This is something that you have to just go outside, look at the sky and train your eyes and understand, right? Because we are just doing in the distance mode this one. And because of the different issues that some of these students have, I cannot force you for few exercises, but I will try to make one that you will go outside and look at the sky and just have some details about two observations, like a record or something like that, right? Then you will get used to it, right? So that's about the a bit about the constellations. And now, so it is also interesting to know that why actually we are concerned about these constellations. Is there any use for us to have the knowledge about these constellations? Is it useful? Actually, this is one thing that comes into my mind is it is very useful to locate other objects on the sky, right? For example, if you are going to look at the Orion Nebula, what you first should locate is Orion constellation. It is what I have uh, here in the slide, right? So when you locate the Orion constellation, nebula is very uh, inside that constellation. So basically to locate other objects, you can use these constellations. Another example is if you want to look at the Andromeda galaxy from a telescope, then first you are going to locate the Andromeda constellation and point the telescope towards that area, right? So those are some practical usages of knowing about the constellations, right? So that's all about constellations, and we will talk more about when it comes to different applications if needed. Then I will move on to the next object that we can visible from our naked eye. That is about the moon. So in this particular section, I will talk about moon, phases of the moon, and also eclipses. Now, for the eclipses, it will mean that we will talk about both solar eclipses and lunar eclipses. And maybe we will not have time to talk about eclipses today, so we will discuss about those maybe tomorrow. But for today, let's talk a bit about the sun, sorry, the moon. Now, orbit of the moon is also actually very nearly circular, right? Eccentricity, you can see that it's 0.05. So which means it's almost circular, but uh, there is I mean, there is a small ellipticity, and the distance from Earth, mean separation from Earth is about 384,000 kilometers, which is somewhat equal to 60 Earth radii. So which means if you fill out 60 Earths on the space, you can reach to the moon, right? So that's the idea. And there is one interesting point here, that is the plane of the orbit is tilted about 5 degrees with respect to the ecliptic plane. So the ecliptic plane is the path of the sun, right? Here, assume that the ecliptic plane is that you see what you see from this red, the yellow color. So that is the path of the sun, and that is the ecliptic plane. And the plane of the or the path of the moon is a bit tilted, right? It's like 5 degrees tilted. Now this may solve a question if you have it in the mind, that when we talk about these eclipses, I I used to have students asking from me, I mean, if you have both these things in a similar path as you see in pictures, why don't we have like lunar eclipses like each month, right? Because the moon complete one circle in each month, no? So there should be a place that the sun, these three objects align each other, right? But the thing is that actually there is a small tilt, like 5 degrees, right? To have these eclipses, there should be places that these orbits crosses each other, right? We will talk about that, right? And before we go into eclipses, let me just talk about these different phases of the moon that we see, because that is obvious. No, we know these phases, right? Now, if I ask you a question, uh, what is the phase of the moon right now? Actually, the phase of the moon, I will show the next one. The the phase of the moon right now is around in the waning crescent, because we know that the full moon is coming towards the end of this month. It should be around like I guess we are still 2 weeks away from the full moon, as far as I remember. Yes. So then, when it is the case, we are in the crescent, right? So let me see how I can see that. Now, in this particular diagram, you can see how phases occur, but there will be a very clear diagram right here. Now, this is also a very important thing that you should know as science students. These are very basic things, how phases of the moon occur, because there are misconceptions in about the phases of the moon as well, right? Now you can see this diagram. In the left hand side, there is a sunlight coming from the left hand side, and the earth is at the center. And you can see that this inner circle, the moon is in between the earth and the sun. And this inner circle, uh, I have placed the moon in a few different points from A to H. So there are 8 positions that I have in this particular diagram. Those are actually places where you have these special names for the phases of the moon, right? And for you should see a very special thing about each of these positions from A to H. You can see that at each time, half of the moon is always lit up by the sunlight, right? The other half is always dark, right? Now this is the reality, right? Now the phases appears because of the angle that we see it. You can see that from point A, we call that as a new moon, because when you look from Earth, me show you from the Earth, when you look from the Earth, you directly see the dark side, right? Because that's a direct angle that you get. But if you go for the opposite side, right here, the point E, you will see the directly illuminated side, right? So that is what we called as the full moon. Now the Earth moves, it takes around 29, or the, you know that this lunar month, it takes around 29 days to complete this one circle for moon. And during that circle, Earth will enter into these different phases, because that how we see the Earth at different positions, right? From here, you can see that at different points, we will see different Earth. From the Earth, we will see the moon from different angles, right? So that's what has happened here. And this is why actually we see different phases, right? That this doesn't mean that the moon is not rotating. Moon is actually rotating, right? I will show that in the next slide. Moon also rotates its own axis, but the rotational period and the orbital period are, I mean, somewhat similar. Because of that, we will see different phases, just because this illumination and the angle that we see. So I have mentioned here the appearance of the moon changes over the course of a complete monthly cycle. the pictures of the moon on the white circle show the perspective from the space. Now these images that I have in outside basically shows what you see at these different positions. And the inside the circle I have in this picture is what actually, how actually Earth is illuminated. Sorry, the moon is illuminated by the sun. But in this, what you see is just the angle. You can see that at this position, you see the first quarter. So which means just a quarter of the moon is illuminated. And you can see that from the new moon, when you go from here to this direction, the illuminated fraction is increasing, and then at the end you will see the full moon, so which means you will directly see the illuminated side, and then after that again the angle changes and the illuminated amount that you see will be reducing bit little by little up to the new moon again. So this is the complete cycle, right? But once again, that is just the angle that we see. Other than that, as you see in this inner circle, in the blue circle, always there is half of the moon is always illuminated by the sun, right? So I have mentioned it here. The outer images show how the moon appears to you in the sky from each point in the orbit. Imagine yourself standing on Earth, facing the moon at each stage in the position new. For example, you are facing the moon from the right side of the earth in the middle of the day, right? So then you will see the new moon, right? So that's what I have explained, right? The next thing is, so that is the, this is again, make sure that you understand this, the reason that you have, why you have these different phases, right? It is just the illumination angle that you see. I mean, different angles that you see this illumination side, right? Depending on how you see it, you will get either full moon, new moon, or this. When you increase the illuminated amount that you see, we use the word waxing, right? So that means increasing. So first you have a small amount just after the new moon, that is called waxing crescent, and then the first quarter, and then waxing givox, and then the full moon, and then you use the name called waning, right? So that means the decreasing the amount. So waning givox, and then with third quarter waning crescent, right? So that's how you uh, use these words. Now actually right now it's just January 11th, so this is I guess 3 weeks. So this is the phase that you should see, the waning crescent, right? Right. Now let's look at how the moon revolves and rotates, right? Which is also interesting. Moon rotates on its axis in exactly the same time that it takes to revolve about the Earth axis, Earth, right? So that's what I have mentioned. When the revolutions it takes, I mean, when if you consider the moon, it also revolves around the earth, and also it rotates around its own axis, but this time it takes to rotate around its own axis and the revolution time it takes to revolve is roughly the same, right? And because of this, moon always keeps the same phase turned towards the earth. You know, these, when these two are equal, you will also see the same phase, right, towards the earth. The difference is the moon's appearance from one night to the next are due to the changing illumination by the sun, right? Not to its own rotation. Right. So this is in a diagram. I can show that to you how this illumination, the rotation, how the moon looks like without and with rotation. So moon actually rotates. Now, if it didn't rotate and if it stay only in one direction, in the diagram A, you can see that we will see different directions or different views of moon because it doesn't rotate, right? And just go like that, and you will see different like directions or different surfaces of the moon at different times. But it is not the case, and this is actually what actually happens. You will see uh, each time when you look from the Earth, you will see the same side because this rotational period and the revolution periods are similar. And in this diagram B or the second diagram, you can see that because it rotates, you always see the same side of the moon throughout the month, right? Because of this equal rotation and revolution periods that it has, right? So that's why this white arrow keeps pointing towards Earth each time because of this, the similarity of the rotations, its own axis, and the revolution, which is interesting, right? Right. Right. So let me. It seems like you. I can see that you probably maybe have a bad weather as well. So if anybody have any questions, I would like to answer. And by the way, my lectures are based on. I actually forget to give you this. Let me give you this link to you. I guess I have posted it last year, but I forget it this time. A reference for you, which is actually completely free to use, and also this is open. There is a website called openstacks.org. Let me show that to you. Right. So my actual lectures are based on the astronomy book in this openstacks.org, and this is a free and open source platform for free ebooks. And this book, there is an astronomy book here, and actually there are other books if you like to use in other subjects. But for me, this is actually an astronomy book that you had. I mean, I would like that everyone use it. This is completely free, officially free, and there is an online book, a PDF, and there is an mobile app that you can use to use this book, right? My actually all the notes are not based on this, but some of the notes actually I keep updating using this book, my old notes. So I did the same thing for today's lectures as well. So it is not the same lectures that I used the last year. I use this book to update some of this stuff. The book is very clear. If you read it, you will understand a lot of stuff. And the only thing is when you are using it in the app, when you download it, you will be prompted asking your university name, and the university name is not there in the list of they have, because this is US based. This is only for like US based universities are using this, but there is an option called other universities. So select that. Then you can use this book completely free and in a nice environment even in your mobile phone, right? If you don't have a computer. So that's why I specifically selected this book, because it can reach to all of you with different facilities. Right? So just go through the book if you like. And some of even these examples that I have taken today are from the book. Uh, so I mean, I would like that you go and refer that book a little bit. It's not that all the things that I am doing from the book, right? So keep that in mind as well. But I used to use this book more and more right now because the different issues that students have, so that they have a good reference as well, right? Uh, that's all. And I can see that one of you have a question. I get the meeting ID. Oh, this he's actually asking that I don't know what this problem is because he is posting waiting for us to start this meeting. I'm not sure about this. Anyway, now actually we are basically done.